Welcome back to Plastic Ingenuity's Thermoform Circularity Course. I'm Sarah Weber, a Sustainable Packaging Engineer at Plastic Ingenuity. This fourth lesson focuses on advanced recycling. When we started our discussion on recycling, we learned that recycling rates vary depending on packaging materials and format. And although 4.5 billion pounds of plastic packaging was recovered for recycling in 2020, that still left 28 billion pounds of plastic packaging available for recovery. Many of these packaging products are not desirable for the current recycling structure. This is where advanced recycling can help drive our industry towards circularity. As we learned in the packaging polymers lesson, plastic packaging can come in many shapes, sizes, and colors. Plastic packaging ranges from PET bottles and thermoforms to polyethylene films and HDPE jugs. It is quite common for packaging to contain barrier layers for moisture or oxygen to extend the shelf life or keep our products safe. Packaging is highly engineered to match a product use, but oftentimes these additive barriers or material structures just don't fit within the current mechanical recycling infrastructure. As sustainability becomes more prevalent within our industry, packaging engineers are working to design packaging for recycling. However, some key aspects to a package make it undesirable for mechanical recycling. Mechanical recycling is an operation aiming to recover plastic through mechanical processes such as grinding, washing, separating, drying, regranulating, or compounding, and thus producing recycled content that can be converted into new plastic products. Now, advanced recycling techniques convert waste that would otherwise be landfilled or incinerated into polymer feedstocks or building blocks and create virgin quality plastics. Advanced recycling aims to create circular pathways for waste that is not compatible with mechanical recycling, such as colored plastics, packaging with laminate barriers, or plastics that are in complicated material structures or formats. Advanced recycling can be called a plethora of things, such as chemical recycling, enhanced recycling, molecular recycling, or feedstock recycling. But for the sake of this lesson, we are going to use the term advanced recycling. The schematic on the screen outlines different recycling processes. Mechanical recycling is the smallest loop in the schematic as it has the least amount of processing involved to create recycled flake or pellets. As we venture further into advanced recycling techniques, we will see the amount of processing steps increase and the outputs change for each process. For mechanical recycling, the output is recycled flake or pellet. For purification, the output is a polymer that is processed into a pellet. The output for depolymerization is a monomer intermediate that is converted into a polymer and further processed into a pellet. And finally, for conversion, the output is naphtha, which is turned into a monomer intermediate, then a polymer, and finally processed into a pellet. Each of these recycled pellets are then used to create new plastic products. Now, I know that was a lot to take in at first, so let's dive in a little deeper to each of these advanced recycling techniques. Purification is a process that involves dissolving the plastic in a solvent, and then separating and purifying the mixture to extract additives and dyes to ultimately obtain a purified plastic. It is important to note that purification does not change the polymer on a molecular level. This process starts with sorted waste, where it is ground into flake and put through a solvent wash. This solvent wash removes any impurities from the plastic, such as colors and additives, and after the solvent wash, the output is a purified flake. The flake is then pelletized into virgin quality pellets and can be converted into new plastic products. The second advanced recycling technique is depolymerization. Common processes under depolymerization are methanolysis, glycolysis, or hydrolysis. Depolymerization involves breaking down large polymer molecules and turning them into smaller units called monomers. Depolymerization is actually the reverse process of polymerization. Polymerization is a chemical process that starts with monomer intermediates. Those monomers are bonded together to form long and often repeating chain-like structures known as a polymer. So in short, polymerization is taking monomer building blocks and creating them into polymers. And then depolymerization is taking those long polymer chains and breaking them back down into monomer building blocks. Those monomer intermediates derived from recycled plastic is what we use to create recycled polymers. The depolymerization process can be biological, chemical, or thermal, and in some cases, a combination of 2 or 3 of these methods. This process starts with sorted waste. The material undergoes a reaction to break those polymer chains into monomers. Those monomers are further converted back into polymers, and these polymers are then pelletized into virgin quality pellets that can be used to create new plastic products. Lastly, conversion is the technique that takes it one step further. The conversion process involves breaking the molecular bonds of the plastic, and the outputs of conversion are hydrocarbons, like the products derived from petroleum refining. These outputs may enter different supply chains, such as fuels for combustion or petrochemicals that can be made into new plastics. Familiar methods under the conversion umbrella are pyrolysis, gasification, or hydrothermal processes. During the conversion process, we start with sorted waste. This waste undergoes a reaction to create a feedstock, such as pyrolysis oil. The feedstock is put through a cracking process, which is a chemical process of breaking large hydrocarbon molecules into smaller ones. These monomers are converted into polymers, further pelletized, and then converted back into new plastic products. Each recycling technology has a desirable material input, which enables a diverse use of technologies. Sortation is still required, and it's an important step for all recycling methods. Purification and depolymerization require the most sortation, and conversion requires the least. For mechanical recycling, PET, HDPE, and polypropylene are all desirable. Purification is targeting HDPE and polypropylene. Depolymerization desires PET, polystyrene, or PETG, and conversion can be converted through HDPE, LDPE, polypropylene, or polystyrene. It is also important to note that for each of these material pathways, using low-value feedstocks, such as MRF residue or waste that is otherwise being landfilled or incinerated, like carpeting, textiles, or healthcare waste, is critical for the economic viability of advanced recycling. When it comes to the economics behind advanced recycling, we have seen significant investments being made to increase capacity of advanced recycling. As you can see on the graph shown on the screen, the share of plastic made from advanced recycling is expected to grow sizably by 2030. Advanced recycling could grow to 20 to 40 million metric tons, or 4 to 8% of the total plastic supply by 2030. This will require more than $40 billion of total investment. We also see mechanical recycling continuing to grow in 2030 and 2040. Mechanical and advanced recycling are designed to be complementary to one another, and growth for both categories will only benefit our industry. An important aspect to advanced recycling technologies is the greenhouse gas impact. So let's compare greenhouse gas impact of advanced recycled materials to fossil fuel-derived materials. The impacts will vary based on specific manufacturing processes or inputs. In many cases, these technologies are still scaling, so the range of greenhouse gas impacts are likely to lessen as years go on. For purification, the impacts can range from 7% increase to a 45% decrease, with the average being a decrease of 20% in carbon emissions. Depolymerization ranges from a break-even point to a 36% decrease, with an average of a 12% decrease in carbon emissions. Conversion ranges from a 22% increase to a 26% decrease, and averages at a 7% decrease in carbon emissions. Incorporating advanced recycled materials into the value chain requires something called mass balance. Since advanced recycled materials have the same quality as fossil fuel-derived virgin plastic, it is impossible to know the difference between the two. Even if you conduct material testing, you can't tell the difference between these two materials or where they came from. So companies need a system to track advanced recycled materials, through their value chains so claims of recycled content can be verified and accurate. A mass balance chain of custody is designed to track the total amount of content in the scope, such as sustainably sourced plastic feedstocks, through the production system and ensure the appropriate allocation of this content to the finished goods based on audible bookkeeping. Mass balance is a common method that is used in other industries such as power grids, agriculture, timber, sugar, soy, and cocoa. So this is how mass balance works. In this flowchart, you will see two inputs, a fossil fuel-derived feedstock and a circular or bio-based feedstock. At each step in the value chain, there will be segregated bookkeeping to track the amount of circular material and fossil fuel material. When the two materials are mixed together to create a final product, a company can create a certified and verifiable claim of the circular materials used. Here's another analogy to explain mass balance. Let's say you get some money from your paycheck, but you also get money from your grandma. All of that money goes into a checking account where it is mixed together. From that point on, you don't know which dollars came from your paycheck or what came from your grandma. All of the money looks the same. When you pull that money out for a few payments, you don't know the exact money that you were using came from your grandma or your paycheck. But through mass balance allocation, you can allocate money from your paycheck to pay for your bills and buy your groceries, and allocate the money from your grandma to buy a new video game. A mass balance system needs to be certified. A very common certification in the industry is ISCC+. ISCC stands for the International Sustainability and Carbon Certification. It is a globally leading certification system that aims to encourage the implementation of the highest sustainability requirements. ISCC Plus is a certification that promotes environmental, social, and economically sustainable production, and is robust proof of traceability of sustainable feedstocks through the supply chain. So why is a certification like this important? Well, mass balance offers solutions that are credible, verifiable, and prevent greenwashing. ISCC Plus provides guidance on allowable marketing claims to avoid greenwashing, and this certification will also ensure a full and unbroken chain of custody throughout the value chain and enables companies to integrate advanced recycled materials easily. So let's run through one more mass balance example using thermoforms as the product. With an ISCC Plus system, resin producers and converters must achieve ISCC Plus certification for each processing unit or facility. Product buyers must register as licensees in order to procure sustainable declarations. Let's start at the resin producer. Say we have 50 pounds of advanced recycled material and 50 pounds of fossil fuel-derived virgin material. During resin production, there is a 10% loss. When the resin is completed, all the pellets are mixed together, and we cannot tell what is derived from fossil fuels and what is derived from advanced recycling. But through mass balance, we can say we have 45 pounds of recycled material and 45 pounds of fossil fuel-derived material. Then that material will come to a converter, like Plastic Ingenuity. So again, we have 45 pounds of recycled material and 45 pounds of fossil fuel-derived material. Through our thermoforming process, say we have a 20% loss. The physical parts will have recycled and fossil fuel-derived material all mixed together. Some parts may have more recycled content and some may have less. But since our inputs are both virgin quality materials, we cannot tell the difference between the two. But through mass balance, we can say that 6 pounds came from advanced recycled materials and 6 pounds came from fossil fuel parts. When we ship these parts to our customer, it will come with a sustainability declaration from ISCC Plus, so our customer can make audible, verifiable, and certified claims for the content. During this lesson, we learned why advanced recycling is innovating the recycling industry and allowing for more materials to be recycled. We dove deep into purification, depolymerization, and conversion. We discussed greenhouse gas impacts and economic landscapes of advanced recycling. We ended our lesson with a mass balance overview, an example of how this process works with advanced recycled materials. In closing, advanced recycling represents a significant leap forward for the plastics industry. It offers a multifaceted solution to some of its most pressing challenges. Not only does it divert plastic waste from landfills or incineration, but it also provides a sustainable pathway to reduce our reliance on fossil fuels by creating a circular economy for plastics. By harnessing advanced recycling technologies, the industry can recover valuable resources, reduce its environmental impact, and promote innovation in material science, all while addressing the global issue of plastic pollution. Embracing advanced recycling is not just a leap in the right direction, but it is transformative in the opportunity to reshape the future of plastics, making it more sustainable, efficient, and environmentally responsible.